You take a coffee cup, it's sitting on the edge of a table, and you're clumsy, like me, often, and you knock it off. It falls, it hits the floor, it breaks. There are pieces of ceramic flying in every direction, little splashes of coffee going up and out. Chaos on your kitchen floor. Now, I want you to imagine, really imagine, a movie of that. Now I'm going to run that movie backwards. The pieces of the cup leap up off the floor. They all rush together perfectly. The coffee pours back in. The cup flies up, lands perfectly on the edge of the table. Everything is fine. You watch this and you say, that's ridiculous. That doesn't happen. That can never happen. And you feel absolutely certain about it. But here's the thing I want to press on you. Why? Why can't it happen? Is it against the laws of physics? That's what you think, isn't it? You think somewhere in Newton's laws, somewhere in the laws of electricity, somewhere in the equations of nature it says cups do not unbreak. But I want to tell you something astonishing. It's not there. You search through all of those equations, Newton's laws, Maxwell's equations, quantum mechanics, and you will not find a single one that says the past is different from the future. The laws of physics at the fundamental level are completely, perfectly, beautifully reversible in time. And yet the cup doesn't unbreak. This is not a small puzzle. This is one of the deepest questions in all of physics. And when you really understand what's going on here, you will understand something important and surprising about time travel, specifically why you can't do it, and why you can't do it is not the reason most people think. So let's start at the beginning. When Newton wrote down F equals ma, he didn't put an arrow on time. The equation works just as well if you run time forward or backward. A ball thrown up comes down. If you run the movie backward, a ball coming up being caught. That's also perfectly consistent with F equals ma. Gravity works the same way in both directions. Electromagnetism. You take Maxwell's equations and substitute minus t for t. The equations are unchanged. They don't care which way time flows. Now this seems like a mathematical curiosity, but it's much more than that. It means that if I showed you a film of two billiard balls colliding, just two of them, and I ran it backwards, you literally could not tell which direction was forward. Every collision at the atomic and molecular level is completely time reversible. If you could somehow reverse all the velocities of every atom precisely, the whole system would run perfectly backwards. It would look like a movie in reverse. And yet every single step would be obeying every single law of physics exactly. Now we have a problem. Because I told you the laws are reversible, but the cup doesn't unbreak. These two statements appear to be in direct contradiction. So what's going on? What is going on? The answer involves a concept called entropy. And entropy is one of those words that gets thrown around a lot, usually incorrectly. So let me tell you what it actually means. Entropy is, and this is Boltzmann's great insight, the number of ways that the inside can be arranged so that from the outside it looks the same. Let me say that again because it's important. Entropy is the number of internal arrangements that produce the same external appearance. Think about the cup sitting on the table. That intact whole cup, there's basically one way for it to look like that. The atoms have to be in just the right positions to form those smooth curved walls, that handle, that particular shape. There's not a huge number of arrangements of the atoms that produce a whole cup. It's quite specific. Now think about the broken cup on the floor. Oh, there are many ways to be a broken cup. The pieces can be in thousands of different positions. The coffee can be splashed in countless different patterns. This piece can be over here or over there. That piece can be flipped this way or that way. There are enormously more arrangements of atoms that correspond to broken cup on the floor than there are arrangements that correspond to whole cup on the table. And this is the key. This is the whole thing. When we talk about entropy increasing, what we mean is systems naturally evolve from situations where there are fewer possible arrangements towards situations where there are more possible arrangements. Not because there's a law that says they have to, but because, think about it, if you have 1,000,000 possible arrangements and only one of them is intact cup, and 999 of them are broken cup in various states of mess, then just by accident, by the pure dumb statistics of randomness, you're almost certainly going to end up in the broken category. It's not a law, it's overwhelming probability. Here's an analogy I like. Suppose you have a box divided in half. On the left side you have a gas, say all blue molecules. On the right side, nothing, a vacuum. Now you remove the divider. What happens? The gas expands to fill the whole box, always, every time. You wait and wait, and you will never see all the blue molecules spontaneously collect back on the left side. Now, is there a law that says they can't? No. Every individual molecule is bouncing around, and every individual collision is perfectly reversible. A molecule going left could go right instead. There's nothing preventing it. But think about the numbers. If you have, say, just 20 molecules, which is a laughably small number, real gases have something like 10 to the 23rd. There are about 1 million possible arrangements, and only one of them has all 20 molecules back on the left. Just one, against 1 million. That's why it doesn't happen. And with 10 to the 23rd molecules, the probability of spontaneous reseparation is so vanishingly small that if you waited longer than the age of the universe, longer than many, many, many ages of the universe, you would not expect to see it happen even once. This is the second law of thermodynamics. Entropy increases, not because God commanded it, not because Newton wrote it down, not because Maxwell put it in an equation, but because there are vastly more disordered states than ordered ones, and systems naturally wander into the more numerous states. Now, let's talk about time. Here's the remarkable thing. The arrow of time, your intuitive gut feeling that the past is different from the future, that causes come before effects, that cups break and don't unbreak, that you remember yesterday but not tomorrow. All of that, all of it, ultimately comes down to entropy increasing. The direction in which entropy increases is the direction we call forward in time. Take any process. You can always tell a movie played forward from a movie played backward by asking, in which direction is entropy increasing? The direction of increasing entropy is the direction of time. Memory works because your brain stores low entropy records of past events, and entropy has been increasing since then. Causes come before effects because the cause is the lower entropy state, and entropy increases toward the effect. Everything you intuitively know about time, all of it, is a consequence of this one statistical fact. And now we can talk about time travel. People talk about time travel as if it's just a matter of finding the right machine, the right wormhole, the right amount of energy. Build a DeLorean, get to 88 miles per hour, figure out the flux capacitor, and you're done. The laws of physics have a no time travel rule hidden in them somewhere, and you just need the right key. But that's not the situation at all. The situation is much more interesting and much more fundamental. Let me ask you a question. Suppose you could travel backwards in time. You arrive, let's say, 5 minutes in the past, in your own kitchen. There's the cup, still whole, sitting on the table. The cup has low entropy. The coffee is neatly inside it. The ceramic is in one piece. But here's the problem. You arrive there, and you are not a low entropy object. You are a human being, an extraordinarily complex, high entropy thing. You're made of roughly 7 billion atoms, all in fantastically complicated arrangements. You have memories. You have food digesting in your stomach. Your neurons have been firing for however many years you've been alive. You have spent entropy to get here. You are a walking record of entropy increasing. When you arrive 5 minutes in the past, you bring your high entropy state with you. You are an isolated pocket of, in thermodynamic terms, the future sitting inside the past. And the laws of thermodynamics, which govern every single atom in your body, still apply. They haven't been repealed. Your heart is still pumping. Your neurons are still firing. Entropy inside you is still increasing. In which direction? Toward your future, which is forward from your own perspective, which means you are sitting in the past, and yet entropy around you is still marching forward from your point of view. You see the trouble? You can't actually go back to the past in the meaningful sense because the past is a thermodynamic state. It's a state of lower entropy. You can't just insert yourself into it because you yourself are a higher entropy object. You would be like trying to take a river and make it flow uphill by placing a waterfall in the middle of it. It doesn't solve anything. You are bringing the future with you. But wait, you say, forget about traveling yourself. What if we just reverse the laws? What if we could reverse everything, every particle, every velocity, every state, and just run the universe backwards? Wouldn't that be time travel? Well, yes, in principle, if you could reverse every single velocity of every single particle in the observable universe simultaneously, the whole thing would run backwards. The cup would unbreak, your memories would unform, stars would unfuse their hydrogen. Yes, that's time reversal, and it's perfectly consistent with the laws of physics. But notice what you had to do. You had to control precisely every single particle in the universe, every electron, every quark, every photon, all 10 to the 80 or so particles, reversing each one with infinite precision. That is not a matter of needing more technology. That is not an engineering challenge you can overcome with more money or more clever engineering. The specification of that task, describing the state you need to set up, would itself require more information than can be physically stored in the observable universe. You'd need a computer bigger than the universe to compute the instruction set. It is, in the most rigorous possible sense, impossible. Not because there's a law against it, but because the statistical improbability is so overwhelming that it is indistinguishable from impossibility. This is the point that I think is the most important one. The laws of physics do not forbid the cup from unbreaking. They are silent on the matter. What forbids it is statistics. What forbids it is the mathematics of probability applied to enormous numbers. And what makes time travel impossible is not some special no time travel rule hiding in the equations. It's the same thing, the same overwhelming statistical barrier. Now here's where it gets even more interesting, because some of you might be thinking, okay, but you just said the laws are reversible, and some very smart people have made that work in interesting ways. Feynman himself, well, I suppose I should not refer to myself in the third person. I myself worked with John Wheeler on something called absorber theory, where we explored a version of electromagnetism that is mathematically completely time-symmetric. And in quantum electrodynamics, there's a beautiful fact. A positron, the antimatter partner of the electron, can be mathematically described as an electron traveling backwards in time. This is not just a metaphor. The mathematics works perfectly this way. So time reversal has real, meaningful content in physics. But notice what it applies to. Individual particles, individual interactions. One electron, one photon, one tiny little quantum event. At that scale, time's arrow disappears. At that scale, backward and forward are genuinely equivalent. The arrow of time is an emergent phenomenon. It emerges from the statistics of large numbers. One molecule, no arrow. 10 to the 23rd molecules, overwhelming arrow. That's the transition. That's where irreversibility comes from. And there's one more thing I need to tell you because it makes the whole picture complete. You might ask, okay, so entropy increases. But why was it ever low in the first place? If everything is just statistical wandering, why did we start in an ordered state that could then become disordered? Who wound up the universe? And this is a genuinely deep question, one that I think requires us to step outside the ordinary laws of physics as we understand them. The answer, to the extent we have one, is the Big Bang. The universe began in an extraordinarily low entropy state, not just a little bit ordered, fantastically, almost incomprehensibly ordered, a hot, dense, nearly uniform state of matter and energy, before stars formed, before galaxies formed, before any of the complex structures we see around us existed, and it has been increasing in entropy ever since. Why did it start that way? We don't know. That is a genuine open question in cosmology and physics, but we know that it did because we can see the consequences. The arrow of time, the fact that you remember the past and not the future, the fact that the cup breaks and doesn't unbreak, the fact that you can go from youth to old age but not the other way, all of it traces back to that one initial condition, that one extraordinarily special starting point. So the broken coffee cup is not just a coffee cup. It is evidence. Evidence that the universe started in a special low entropy state. Evidence that entropy has been increasing ever since. And evidence beautifully, completely, without any need for a special no time travel law, that going backwards in time in the meaningful macroscopic sense is not something the universe does. Now, people sometimes ask me, well, what about the movies? What about H.G. Wells? What about Einstein's relativity? Time dilation? Doesn't that allow time travel? And I want to be careful here, because there are things in relativity that do genuinely do something with time. If you travel very fast, your clock runs slow compared to someone standing still. You can, in a sense, jump forward into the future, travel fast for a year, come back, and find that 100 years have passed on Earth. That's real. That happens. That's been measured with atomic clocks on airplanes. This is relativity's version of time travel. But notice, it only goes forward. The relativistic effects slow your clock, meaning you experience less time while the world experiences more. You arrive in the future. You cannot arrive in the past. Relativity does nothing to help you go backward. And why? Because going backward means decreasing entropy. It means going from the broken cup to the whole cup. And all the time, dilation in the world doesn't change the fact that entropy in your body and the world around you is still ticking forward. There are exotic solutions to Einstein's field equations, wormholes, closed time-like curves, exotic geometries that are sometimes presented as possible time machines. These are fascinating mathematical objects. I enjoy them very much as mathematics. But even in these cases, when you work through the physics carefully, you run into severe problems. Not just engineering problems, fundamental problems. Problems with causality, problems with consistency, and ultimately, problems with entropy. The universe seems to have a profound reluctance, not a law, but a reluctance to allow situations where the thermodynamic arrow is violated at a macroscopic scale. And I find that beautiful, not because it closes a door. I always find it a little sad when something turns out to be impossible, but because of why it's impossible. It's not impossible because God said so. It's not impossible because some physicist sat down and wrote an equation that said no time machines. It's impossible because of the same counting argument that tells you why your coffee gets cold, why your perfume spreads across the room, why you cannot unscramble an egg. It's impossible because of numbers, because of the terrifying, overwhelming, almost silent power of large numbers and statistics applied to the particles that make up everything. The broken coffee cup is a window into the deepest nature of time. When you look at those pieces on the floor, you're not just looking at a mess. You're looking at the arrow of time made visible. You're looking at the reason the universe is not the same going forward and backward. You're looking at the reason time travel, real, backward-going, past-visiting time travel, will never work. And the reason is not that we haven't built a good enough machine. The reason is that the universe keeps score. It counts the arrangements. And it always finds that there are more ways to be disordered than to be ordered. And so it goes there, inexorably, overwhelmingly, and, to my mind, wonderfully. That's the story of the coffee cup. That's the story of time. And I think it's one of the most remarkable stories in all of science.